All right, today we are going to talk about TinyEngine, okay? So efficient training and inference engine on microcontrollers. So we have learned a couple of algorithms techniques that including TinyNAS, OS4 network, okay? And also those training on with 256 kilobyte of SRAM, right? So today we are going to talk about how to write fast kernels, okay? Fast kernels, memory efficient kernels, so that we can fit those tiny models on microcontrollers, even lower level than what we have learned so far in the optimization stack. Okay? And our key idea is to perform its full stack optimizations across algorithms, systems, and hardware. Right? So this is the agenda for today. Okay, it looks pretty dense, but it's very well organized. So we are going to first introduce what are microcontrollers and why they are essential. Right? Since microcontrollers is the device we're going to use in Lab 4, so hopefully this gives you some high-level idea what they are and also how do we program them. Okay? And also we're going to talk about these critical factors of deploying neural nets to microcontrollers. What is their memory hierarchy? What is the data layout of our neural nets? And the part 3 is the major component for today's lecture, okay? Critical optimization techniques, the implementation details of TinyEngine, including this general and very classic optimization techniques like loop unrolling, reordering, loop tidying. All these are centralized around efficient memory and reducing the data movement, since we have learned that computation is cheap, memory movement, data movement is expensive. Right? So we are going to do these techniques like tidying, reordering to reduce data movement, SIMD, image to column conversion, in place depth-wise convolution to reduce data movement, different data layouts, okay? And finally the Winograd convolution. So you are going to experience and try to play with these techniques in Lab 4. So it'll be quite an interesting lecture. So let's get started with the first part. Okay, what are microcontrollers and why they are quite essential? So introduction to microcontroller, very low cost, low power, and they're growing very rapidly in recent years. Okay, the amount of microcontrollers with the year is getting pretty increasing pretty fast. A lot of applications, personalized healthcare, agriculture, smart home, etc. And they are widely used in a lot of applications, such as in vehicles, okay, in the autonomous driving vehicle, or even conventional vehicle for various control. There's a lot of microcontrollers inside. Okay? And robotics, office machines, vending machines, medical devices, mobile radio transceivers, vending machines, home appliances like in your refrigerator, your washing machine. It's very likely that one of in these devices, in these appliances, one of such microcontrollers is inside, right? So there are several dozen of microcontroller architectures and different vendors. They're mostly ARM-based. Okay, so STM32 is a 32-bit microcontroller we are going to use in our Lab 4. Okay, there are also other vendors, including from TI and also from Microchip. So they are mostly ARM architecture. So it's a very simple miniature personal computer, right? So without operating system. So there's no paging, no memory management. So we are going to play with the bare metal to manage everything by ourselves. So there are several advantages, right? So for these microcontrollers, very cheap, low cost. They are usually manufactured with older technology like 16 nanometer, 28 nanometer. So it's very cost effective, relatively low power, and with small, cheap area. But in the meantime, there's no free lunch, So usually we suffer from low computational power on these microcontrollers, okay? And very low memory and storage space. We are soon going to visit the amount of capacity for storage, for memory available on these microcontrollers. And also there's limited amount of instructions available on such microcontrollers. So That's advantage and also disadvantage. So a microcontroller usually have the below components. So of course can contain the CPU. Okay, usually it's an in-order CPU that is low power, easy, and less complicated pipeline, right? With some volatile memory, which is the SRAM. Usually a couple of no more than a couple of 100 kilobytes of SRAM. So very little SRAM. Also have some non-volatile memory, maybe 1 to 2 megabytes of flash memory. Okay, and also several I/O ports, peripherals, ADC and DACs. So here's give you a rough comparison between the STM32 F746 MCU, which you already have one of them at home, right? We gave you those board for Lab 4, which is going to be released today. Okay. This is the board we are going to play with, and this is Apple MacBook Pro with M1 Ultra, right? So we are comparing the CPU cores, the cache, memory capacity, etc. Right? So here, the number of cores is roughly single core versus Apple MacBook Pro. M1 Ultra has 20 cores, right? So one is clocked at about 216 megahertz, while the other is 3 gigahertz, right? An order of magnitude difference in the clock frequency. So what's the benefit of that? Low power, right? Since the power consumption is proportional to the frequency, right? It's CV square F. C is the capacity, V is the voltage, and F is the frequency, right? So low power due to low frequency. And also no GPU core, of course. Neural engine, no neural engine on microcontroller versus 32 neural engine cores on the M1 Ultra. L1 cache size super small, only 8 kilobytes of SRAM for L1 cache versus 320 kilobytes. Only one level of cache, no L2, no L3, versus on M1 Ultra, there are as much as like almost 100 megabytes of L3 cache, which is pretty big. Memory capacity, there is no DRAM. So only at 320 kilobytes of SRAM that is both readable and writable, versus the storage, you have only 1 megabyte of read-only read-only flash. Okay, you can program it offline, but the writing overhead is pretty big, versus 64 gigabytes of DRAM and terabytes of storage, right? With operating system, without operating system. Okay, so we have to be able to manage everything by ourselves without an operating system. And the memory capacity is several orders of magnitude smaller compared with a laptop CPU. Just give you an idea how small and how low the resource we have. Okay? A basic intro about the memory hierarchy, which you might have learned in 6004 or in other computer architecture courses. Right? So the fundamental principle in computer architecture is that computation is cheap. Data movement is expensive, right? We want to have a both larger memory and also low latency, right? So there is no free lunch. If you have high capacity like SSD or HDD, you have very long latency, right? But if you want a low latency, like in registers in L1 cache, it's pretty expensive, right? So we have 6 transistors for SRAM cell versus only 1 transistor in a DRAM cell, right? So how do we have the illusion we have both a large memory space and also a fast memory? So that is by using cache. If we get a cache hit, we can benefit from having a very low latency, right? But the size also is pretty small for these L1 and L2 caches. So today we are going to learn by using blocking techniques so that we can enable a better cache locality so that we can hit L1 cache as much as possible, if not L2 cache as much as possible, rather than having to go to the DRAM memory. So in comparison, so this is the personal computer laptop versus a microcontroller, right? So we have a couple of levels of L1, L2, L3 cache versus only one level of cache on a microcontroller, right? And the size is also differs a lot, hundreds of kilobytes versus only 8 kilobytes of L1 cache. And there's only one level of cache, and then we have this 320 kilobytes of SRAM, which is writable and readable, both writable and readable. And then we have 1 megabyte of flash, which is read-only. So question here, if we want to deploy deep neural net for inference, for the weight and for the activations, where shall we store them in the microcontroller? Is it in flash or is it in the SRAM? Right, exactly. Since the flash is read-only, the weight should be in the flash, but activation, we should be able to read and write it. Therefore, it can only reside in the SRAM. Since we have only 320 kilobytes of SRAM, what's the maximum activation we can have? It's very clear, right? That's the peak memory we have available. Considering the input activation, output activation, you have roughly, if you divide it by 2, roughly 160 kilobytes for a tensor. And you can quickly calculate what is the dimension and how many channels you can fit. Right? Remember, the way to calculate the activation size is resolution X by resolution Y by the channel. Right? So you can easily calculate how many channels and how much, what size of the resolution you can fit given such a tight memory budget. Okay, therefore, how to effectively utilize the L1 cache is one of the most critical factors to boost the performance of your code on a microcontroller. Okay, so we learned these basics. What is the available resource? What is the memory hierarchy for microcontrollers? And then we are going to talk about neural networks, the critical factors of deploying neural nets given such resource constraints, especially memory resource constraints. Okay? And why deploying neural networks on microcontrollers is challenging, and also how should we lay out the data in microcontrollers. Deploying neural nets on microcontrollers is challenging because existing neural nets like Resident 50, MobileMV2, or the quantized version of MobileMV2, which is 4 times smaller than the FP32 version, is too big to fit the memory constraint, especially the SRAM constraint, right? Since we mentioned there's only a couple of 100 kilobytes of SRAM in microcontroller, and that's the only readable and writable memory that we have. Flash is read-only, right? So that's the peak memory constraint. Versus for these neural nets, they demand a pretty large, pretty big memory resource, as much as 7 megabytes, right? Therefore, the techniques like we mentioned, like quantization or pruning, neural architecture search, plays a very important role here. But even after quantization, it's still like 5 times bigger. So conventionally, people can do such toy examples, classifying apples and oranges under low resolution, right, on microcontrollers. But MCUNet, including TinyEngine that we will discuss later, enable us to do ImageNet level classification, reaching 70% top-line ImageNet accuracy on a microcontroller. Question?
The flash memory, is that programmed exactly once and then can never be changed again for a given microcontroller?
Yeah, it's programmed once you are at the programming time, and then writing to that is super expensive. Particularly for microcontroller, but for like USB drive, that's also flash. That flash is off chip, but this flash is actually on chip. So that's why the characteristic is different. It's a single chip that contains everything. Okay, so this is back to our previous question. Given a neural network, we have weights, we also have activations. Where do we store the weights and activations? We already discussed that. We have to store the weights in the flash. Okay? And when we are calculating a certain layer, we just bring the weights of that layer to SRAM when we are processing that, right? And since these activations need to be readable and also writable, we can only store them in the SRAM, which is about 300 kilobyte or 256 kilobyte, depending on the microcontroller that you are using. So since memory is the key bottleneck of deploying deep neural nets into microcontrollers, we are going to talk about several data layouts. How do we store these weight and activation tensors in the microcontroller? What are the choices? And which one would be more expensive and which one would be cheaper? So let's brainstorm a little bit. How should we store those tensors? For weight and for activations, they are both how many dimensions are the weights and activations? Imagine a batch size of only one, since we are doing real-time processing. What's the dimension for the weight and activation for each layer? 4 and 3. Right. So for weight, we have input channel, output channel, and kernel X, kernel Y. Right. So that's 4-dimension tensor. And for activation, we have X, Y, we have channel. Right. So that's 3 dimensions. So this is a representation of actually a 4-dimensional tensor. Okay. So this is X, Y, and the number of channels. Okay. And we have 2 of them. Maybe the output channel dimension. Okay, so this is the input channel dimension. This is 2 output channels. Therefore, we have 4 dimensions for the weight. And there are several ways to lay out the weight and activation is kind of tensors in the memory, right? One method. So here, let's first discuss the terminology. N stands for the batch dimension, so outer dimension. It can mean for the activation, it can mean the number of images, the batch dimension, and for the weight, it means the output channel. How many kernels do we have, and how many output channels do we have? So that's the N dimension. We also have the C dimension, which is the channel dimension. Okay, so for weight, that is exactly the input channel dimension. Okay, for activation, that is just the channel dimension. And H and W for activation, that's the resolution, H and W. For kernel, that's the kernel size, okay, 3 by 3. Okay, 3 by 3 or 5 by 5. So NCHW means the height and weight dimension are in the inner loop. And C is the next order, and N is the outside, right? So here we made a animation to represent that. If you have NCHW, if first element is here, so this is the H dimension, this is the W dimension, this is the channel dimension, and if we repeat that, we have the N dimension, right? So if we have NCHW, the inner loop, the dimension that is changing the fastest is actually the W dimension. Therefore, if we increment the pointer by 1, we are actually proceeding in the W dimension, okay, since W is to the right. So after we fill in all the W's, we go to the next H dimension. And after we fill the entire 3 by 3, we go to the next channel, okay? Next channel. So we go to the next channel, okay? And continue on the W dimension, and then H dimension, and then we move forward to the next channel. Okay? Finally, we fill in all the channels within a N, and then we move to the next N dimension, okay? The next N dimension, and restart from this H and W, and then another C, and then another C, all the way to the end. Okay, so this is the data layout for NCHW, which is used by default by Caffe. Any of you have heard of this tool called Caffe? Some of you maybe. When I was doing PhD, basically there's no PyTorch, no TensorFlow yet. That was in 2015, 2014, right? So Caffe was at that time the most popular infrastructure, the tool that we use to train neural nets, and this using the NCHW data layout. There's another one, right? So NHWC format. So how does that look like? We have the C channel or the channel dimension in the inner loop, right? Meaning that this is the first dimension we are going to have the consecutive data layout. So if we put the first number here, where should we put the second number? Next channel, yeah. Then 001 should be put here, right? And then similar for the next number. So they are labeled in different number, but this is showing the sequence in the memory layout, right? So we are actually having its neighbor data in the memory layout is actually 009, right? And after that, we move to the next W, right? In the C channel and fill in the entire C channel, and then we start with the next W. And after we fill all the W, we go to the next H dimension. Okay, fill in the entire channel, and then the next W, and next H to fill in the entire C channel, Okay, so anyone can guess what is the advantage of having consecutive data in the C channel dimension for consecutive data? What kind of convolution might benefit from such data layout? The other one, pointwise, right? Since pointwise is actually doing the reduction in the channel dimension. So pointwise, we are doing a reduction of the entire channel, right? Have a one-by-one convolution, and there's no spatial locality, only the channel level locality, right? We want to do a matrix vector product to project this channel to another channel, right? So such NHWC format, which is used by default for TensorFlow, is good for channel-wise reduction. Versus if we have this NCHW, since H and W, the spatial locality is better if we use 3x3, 5x5, 7x7, those spatial convolutions, right? Okay. So this is just finishing up all the animations in the channel dimension. And finally, there is a very rare data layout called CHWN format, where N is actually in the inner loop. So if in that setup, okay, 000 is here, and the next one in the adjacent in the memory is actually in the next batch. Okay, so if it is the weight, then it will be in another kernel, right? And then we are going to lay out in such a format, building the entire channel. Okay, and then we move to the next channel, the first N and then the second N, and fill in this channel as again. And finally, we go to the last channel, the first N, and then first N equal to 0, N equal to 1, 0, 1, 0, 1, etc. This is very rarely used, though. So the key interesting part is that different circumstances require benefit from different data layouts. For example, pointwise convolution will benefit from such NHWC data format, while depthwise convolution, which requires this spatial locality, will prefer this NCHW format. So that's something to keep in mind by looking into your workload, you can specify what kind of data layout is better for your case. And data shuffling is actually quite expensive. All right, so we introduced these two backgrounds. One is related to microcontroller, what is the memory hierarchy, what is the constraint, and then we also introduced the workload, the neural networks, and we talk about different data layouts for the tensors. Now we can mingle these two together and talk about how do we efficiently map this neural network, these tensor operations onto the microcontrollers, which we are going to introduce this TinyEngine. Okay? So there's a lot of concepts we are going to introduce. So I'm going to go relatively slowly to talk about these optimization techniques in TinyEngine. Before we jump into the details, TinyEngine is fully open source. So if you have a laptop, you can go to the GitHub and try to search for MIT HiLab TinyEngine. So that all the code is available over there. Since in this lecture, we also gave you all the code for you to use TinyEngine to do a real-world demo, right? So we didn't give you a lot of code writing assignment, but we do have a lot of good ideas you can pursue for your final project. For example, implementing a few other kernels. If you're interested in this direction, feel free to contact me or the TA if you want to dive deeper into these techniques. So this is the recipe we are going to talk about today. Right? There are roughly a couple of techniques, 8 or 9 techniques that we can use to boost the performance of deep neural nets on microcontrollers. Actually, there are 8 techniques. Okay? I believe in our assignment, we gave you 7 techniques to try. So let's get started with them one by one. First technique we're going to introduce is loop unrolling. Working with tensors usually boils down to writing a multiple for loops. For example, writing a matrix multiplication require 3 for loops. Writing a matrix, writing a 3D, the normal convolution is 6 for loops, right? So we're going to first talk about several techniques related to loops, including loop unrolling, loop reordering, and also loop tidying. Okay, so and then we are going to talk. These are mostly focusing on branch instructions and also memory. And then we are going to talk about this data, right? Single instruction, multiple data. Since in computer architecture, the payload is actually doing the computation, but the overhead is really doing with these instructions, avoiding those instruction overhead. So we want to try to amortize this instruction overhead by having one single instruction that can rule multiple data, right? So SIMD technique. Another technique with respect to data layout, using the image to column technique to convert this convolution into what we already have, which is matrix multiplication. Okay? So matrix multiplication is very widely used, super well-developed kernel. Right? Can we use existing convolution kernels, existing matrix multiplication kernels to implement convolution? So that's image to column convolution. And then we are going to talk about another technique for depth-wise convolution, since depth-wise convolution is just so widely used in these memory constrained places, thanks to the depth-wise convolution. We are going to talk about the data layout for point-wise and also for depth-wise convolutions. Finally, there is a very interesting algorithm called Winograd convolution, which actually can reduce, by theory, reduce the number of multiplication and adds for when you're running neural nets. However, that will explode the weight, which is not feasible for microcontrollers, which has only 1 or 2 megabytes of flash. So that's why this is the only technique we don't have in our lab. But all the about 7 techniques, we're going to see them in the lab. It'll be very interesting. So take the lecture and then go home to take the lab to reinforce what we have learned in the lecture. So that's how we design the lab. Okay, so let's start with the first technique, loop unrolling. So what is loop unrolling? Given a give a piece of code that has 3 for loops, right? So what are the overhead over here compared with without any for loop, just the instructions? We have to deal with the pointers, right? We have to check the boundary for I, for j, for k, whether it's smaller than n, right? We have to do the loop tests. We have to manipulate the pointers, and also we have to do the branch prediction, right? So in computer architecture, the program counter, short for PC, is usually PC plus 4, jumping from one instruction to another to the next one sequentially, right? So when we have such for loops, we have to have such conditional branches, right? Conditional branch means that we have to test if we are larger or smaller than a certain value. If a certain criteria is met, we have to, instead of PC plus 4, we have to jump to another location in the code, right? So in order to avoid those bubbles, if we have a we have to, usually there is a very deep pipeline in the computer, right? So we cannot wait for the ALU to give you the result before we want to fetch the next instruction. Therefore, the branch prediction becomes important. Although we don't know whether we are going to just use the next instruction or we are going to jump into a previous instruction, we just predict we are going to do one of them. But such prediction has overhead, especially when the prediction is wrong. You have to flush the entire pipeline to restart at the correct location and squash those wrong predictions, right? So that's the branch prediction overhead. Loop unrolling is actually be able to reduce those overheads by reducing the number of loops. A question here?
For a for loop like that, where it's just going through a range of numbers, won't the branch prediction fail only exactly once? That's just when it hits the end of the loop.
If the loop is very regular, so the overhead is actually not large. Maybe just during the very end of the loop, right? But if the kernel size is pretty small, loop is just only 3, that is also non-trivial, right? Or if after a lot of pooling, the resolution becomes 7 by 7, that's also not a big number. Initially, you have 224 by 294, 128, 112 by 112, finally only 7 by 7. Okay. So what does loop unrolling do? So this is the original matrix multiplication for loop. Okay, ijk, aik times bkj. We have a common k in the middle. They get canceled, so we get cij. Right. So if we unroll this by 4, the k is no longer with step size of 1. Right now it's with step size of 4. So with every k here, we are going to do 4 operations rather than 1 operation in the loop. Okay, with every k, we are going to calculate aik, bkj, as well as k plus 1, k plus 2, and also k plus 3. Right. So in this case, we are reducing the number of pointer operations from n squared to the one quarter of n squared. And the number of loop tests also reduced to only 1/4 of the n squared. But what is the overhead here? There's no free lunch, right? So the code size, okay, of the most inner loop is actually the size is actually 4 times as its original size, because previously we only write a single line of code. Now we need to write 4 lines of code, right? So each line of code is probably taking 32 bits. That's 4 bytes. That's not a big issue at all for like desktop computers. But for microcontroller, we have only 1 megabyte of flash to store everything, including the code segment. So that could be a pretty big issue if the code size is too big, right? So there's no free lunch. There's always some trade-off. Okay, so that's loop unrolling to reduce this branching uh, this branching overhead, right? And next we have this loop reordering, right, which is a loop transformation technique, so that we can optimize the program's execution time by reordering the sequence of the for loop. So let's look at this example again. So for ijk, we are accessing the A matrix, okay, and also the B matrix, right? So if we are accessing them in AIK and BKJ manner, but K is inside J, J is inside I, right? So if we do AIK, which one is the inner loop? K is the inner loop, right? So we are actually doing row-wise access of the memory. But for B, okay, so J is the inner loop. Actually, K is the inner loop. Okay, so this dimension is actually the inner loop. So we are actually accessing them in a column-wise manner. Okay, so if we store the data in the row-wise manner, but we are accessing them in a column-wise manner, then we have poor data locality, because B00 and B10, they are not contiguous stored in the memory, right? So that is pretty bad. Okay, so the rule of thumb is data movement is more expensive. So usually if you have a cache line, if every number is only 1 byte, so this is a 4 numbers is 32 byte. Okay, if you have a cache line of 64 byte, then it can simultaneously store 8 1 byte numbers, right? So it's likely if you bring in B00, B01 is also brought in the cache line, right? Since each cache line can contain multiple components due to the spatial locality. And if you bring in B00, you may as well access everything after that, which is contiguous in memory. However, B10 is not, right? It's not contiguous in memory. Therefore, if you access them at the same time, it's going to bring in another cache line, which will probably kick out some of the previous cache lines due to the poor locality. Okay, so that's why when we have the scenario where we have a cache line and it's more beneficial to continuously access the memory. Can we change that locality issue? Actually, we can reduce the cache miss by reordering the loops. For example, rather than having I and J, J and K, here we can have K and J instead, right? So if we reorder the loop, J becomes the inner loop. Okay, so J becomes inner loop, and K becomes the outer loop. Okay, in that case, we are accessing the B matrix in the row-wise manner, which makes it has better cache locality. Right, so there's usually such consideration about the cache line versus data locality versus the loop order. Okay, let's continue our discussion about TinyEngine. A brief recap about the big picture, right? So we have very scarce resource, very little resource on microcontrollers. Therefore, the memory footprint is very important. We want to reduce the memory footprint and utilize cache locality as much as possible. And also, our goal is to deploy deep neural nets on these microcontrollers. One way is, of course, you can use the existing libraries like TensorFlow Lite, Micro, etc., to do the inference. But the most efficient way actually is to write your own kernel that take advantage of all these techniques, all these considerations, removing those branching overhead, and taking advantage of the memory locality and SIMD operations, and also these transformations. Right? So we're almost there. We already learned two techniques. One is loop unrolling, and the other is loop reordering to improve the cache locality and reduce data movement. The next technique we're going to introduce is the loop tiling, okay? So which is loop transformation techniques that can reduce the memory accesses by partitioning the loop iterations into small chunks. So each small chunk can fit in the SRAM, in the cache. Okay, say this is a pretty big matrix of size n. So the total accessed element, your memory, also called the memory footprint, is pretty big. It could be as large as n squared, right? For example, AlexNet for the last FC layer is 4096 by 4096. So that's 4K by 4K. That's altogether 16 million numbers you have to access. So 16 million is pretty big. It's way larger than what we have for a couple of kilobytes, right? Therefore, the idea is to block, to just do computation on a smaller subset, a smaller chunk of such data, such that a smaller chunk can fit the cache size. Okay? Initially, the dimension is larger than the cache size, but we want to partition the loop. Okay? So we can fit a smaller chunk of that so that they can fit into the cache. Okay? And also ensure we just work on a small footprint so that the footprint is smaller than the cache size. For example, we can, rather than working on the entire matrix with 3 loops, now we introduced one extra loop for this j dimension. Okay? Previously, we have j dimension. Now we have another dimension for j, another for loop for j, okay, with a larger step size. So we are basically dividing in the vertical dimension with several chunks. So rather than previously we have n squared, now we have n by the tile size of memory footprint, which could be much larger, smaller if tile size is smaller than n. Does this solve the problem of large n versus small cache size? If n is pretty huge, this still cannot fit in the cache size, right? Therefore, we can do tiling in another dimension. Previously, we just did the tiling in the j dimension, okay, j dimension. Now we also want to do the tiling for the k dimension. Okay, we have 2 k's in the loop order, and now we chunk not in the vertical dimension but also in the horizontal dimension, right? So now rather than using n times the tile size of memory footprint, what is the new memory footprint? It's tile size square, right? It's much smaller for the B matrix. But for A matrix, it's still only partially solved the problem, because rather than n squared, now it is n times the tile size of memory footprint, right? So if n is pretty big, this number could also be pretty large. So what's the solution here? If we want to fit both A and B in the cache, we need to do another tiling, right? So previously we tiled J, okay? We tiled K. We should also tile I. Okay, so these 3 for loops become 6 for loops, so that even for A, previously that require n by tile size, now it's tile size square, right? So the memory footprint is no longer related to n, but is just related to the tile size. If we make this tile size square, considering all the matrices, together they can fit within the 8 kilobyte of L1 cache of a microcontroller then the locality of your program becomes much better. So this is pretty simple for microcontroller. This is it. But if we have multiple levels of, so this is the summary, right? So we reduce the memory footprint from n square to tau size square for both A matrix, B matrix, and also the C matrix. And how do we determine this tau size? We just make sure the memory footprint, you add them together, is smaller than our cache size. Like we mentioned, if we have multiple levels of cache, for example, L1 cache is 8 kilobytes, but maybe L2 cache is bigger, then what do? We want to further, for example, the inner 3 for loops, we want to fit everything in the L1 cache. And then if we add another for loop, we want to make sure the tile2 size, okay, times the tile1 size can fit the L2 cache, okay, on and so on. So we add another tile loop. So previously we have 6 loops, now we have 7 loops. We just continue do multi-level of tiling to fit multi-level of cache sizes. So a lot of manual tiling and determining the tile size is pretty cumbersome. There's also such automated tools that I highly recommend you to try, such as TVM, that can perform such tiling automatically for these tensor programs, which is quite useful. Okay, so the next concept is actually SIMD, very widely used.
Yeah, a question about the previous slide.
Yeah.
So about the cache tiling, I'm wondering, is it common to use, for example, cache oblivious approaches?
Cache oblivious approaches for the motivation of protecting your data, or I'm not aware of actually. To protect the motivation is like you have some sensitive data, you wanna. What is the motivation here? Oh, independent of the cache sizes. We can discuss that offline. I'm not quite aware of those stuff. Okay, so next is SIMD techniques. So we know those instruction overhead is pretty big, right? We have to determine which PC do we fetch next, right? And also the dependencies, whether we can reorder the instructions to do out of order execution and to do a lot of predictions and also speculations, right? If the speculation is wrong, we also have to squash all the instructions that are wrongly fetched into the pipeline. And as the pipeline gets deeper and deeper, those overhead could be pretty big, right? So we want to amortize those instruction overhead. You fetch one instruction, but you execute on multiple pieces of data, right? So that's the idea of SIMD. Before introducing the details, let me start with the background, right? So introduce what is the instruction and what is the instruction set architecture. This is just a reminder of the 604. If you have taken it, it should be pretty straightforward. So instruction set architecture is the contract between the software and the hardware. Contract means the policy and also the rules, how to write programs, and also how is that translated to the machine code, right? So it gives you the abstraction of the hardware by such instruction set architectures. This is an example of an instruction set. You can have those arithmetic instructions like add and subtract and multiply. These compare instructions to compare to return 1 or 0 if it's larger or smaller. And then you have this branching overhead, including those unconditional jumps. You just jump to a designated PC versus those conditional branches where you first compare two registers. And depending on the result, you are going to either jump or continue fetching PC plus 4, right? And then we are going to have this load and store instructions to manipulate it with memory, to read and write from and to memory. Finally, we have these I/O instructions. Okay, so I/O for a device, including the monitor, the keyboard, etc. Category-wise, there are roughly two categories of ISA. The CISC, standing for complex instruction set computer, versus the RISC, which is reduced instruction set computer. Right? So for CISC machines, you have many big and specialized instructions. Some of them might be only rarely used, though. Like Intel x86 is using using CISC, and for RISC, each instruction is pretty simple. It can do a very smaller amount of work, but we can have multiple of them. Okay. Our example, like adding two numbers for a CISC instruction can be just one giant instruction that does both memory access and also arithmetic operations, versus a RISC architecture. You may do them separately, right? Load A and B, add them together, and finally store them back to the registers. And for microcontrollers, we are using this RISC instruction set architectures. Since we talk about those instructions, there's no free lunch, right? You have to pay those instruction overhead to do those arithmetic operations, which is multiplication and also multiplication and addition in tensor operations for neural networks, right? So we want to do a single instruction on multiple data, right? Since the computational workload for deep learning is highly deterministic and it's very regular, right? Not to mention those sparse workload is separate, but for the unpruned model, it's really a dense model. And dense workload, the operation is operated on consecutive data, right? So therefore, we can easily do the same thing, lockstep for A1, for A0, B0, A1, B1, A2, B2, A3, B3, right? So we write one multiplication instruction. Previously is operated on only a single piece of data, A and B. Now we operate on 4 pieces of data at the same time in lockstep. So that is called the SIMD. Okay? That is available on mostly all current processors. You just need to find their menu to find their detailed instruction how to use this ISA. For example, this is the conventional code implementing this matrix multiplication. We need n to the power of 3 arithmetic operations. But with SIMD, with one instruction, we can actually do 4 matrix. We can do actually 4 element-wise multiplication and additions. Right? So arithmetic operations is reduced by 4 times. Right? So here we are using the SIMD intrinsics. So the instruction is called SIMD intrinsics. Okay? So every time we are actually doing 4 elements using just one instruction.
Also, the microprocessor supports computing for multiplication in a single cycle.
Yep, computing multiple multiplications in a single cycle, right? And if we reduce the number of bits, for example, rather than 128 bits, if you reduce each number, so here each number is represented by 32 bits. If you reduce the number of bits, the number of operation can be even larger. Okay, so the next technique we are going to introduce is called the image to column convolution. Right? So, those matrix multiplication is very widely studied, and there is a lot of high performance matrix multiplication kernel. So the key idea here is, can we use rearrange the data so that we can directly utilize the existing matrix multiplication kernel to implement convolution? Okay. So this is our setup. We have the activation, we have the kernel, we have the output. Okay. So the input activation has multiple channels, and this is the XY dimension. Kernel size is 3 by 3. The input channel, we have 3 input channels. Okay, we have 4 output channels and 4 kernels in this case. And we are going to do how are we going to rearrange the data format so that we can cast such 6 for loop convolution problem into a three for loop convolution matrix multiplication problem. For example, here, this entire 3 by 3 by C, this chunk of data, will be have dot product with this entire 3 by 3 by C kernel. Okay, we are going to repeat that for all the kernels. We are also going to repeat that for different locations. Okay, move by one since due to convolution. This is actually quite similar to matrix multiplication if you flatten this piece of data rather than 3 by 3, you flatten that by 9 by 1, right? And let's see how that works. So you flatten this entire 3 by 3 piece of data into a 1 by 9 tensor, right? So from A to M. Okay, so here from A, B, C, this is F, G, H, this is K, L, M, right? So from A to M, we flatten that into a 1D array here, right? And then when it moves to the next location, that will be B, C, D, G, H, I, L, M, N. Okay, so from B to N, we flatten that into a 1D tensor. This contains 9 elements. Okay, so whenever we move by one window, okay, we have another row here, right? So this is just the first input channel. We're going to do the same thing for the second and the third input channel in green and also in orange. Since for the convolution, it works that all the elements in the C channel will be reduced, right? So all these elements, 3 by 3 by C, they're going to be reduced to a single value. So all these numbers multiplied by all these numbers will be reduced into a single value. So that we can construct this tensor. Y is K squared C, because we have kernel square, okay, 3 by 3, and the C is the number of channels. Okay, so we are reducing all these K squared C elements into one element. So this row multiplied by this column is reduced to one element. Okay, so this is about activation. How about the weight? How do we reshuffle or shuffle the layout the memory for the weight? So here we have 4 kernels in 4 different colors, right? So we can talk about each kernel separately. So starting with the green kernel, okay? For the green kernel from 0 to 8, we're going to lay them out vertically in memory so that it can be have a dot product with the activations, right? So this dark blue is going to interact with the light green over there. So this dark blue is going to interact with the light green right here. Okay? And similarly for this green, we interact with the green color here, because this green color is also interacting with the dark green color over there. So how many elements are there in the column? It's also K squared by C, right? Since they are doing the dot product, the number of elements for the activations and the weights, they are the same. Okay? And how many dot products do we have to do? This row by this column produces only one element. Right? Since we have 4 such kernels, okay, green, red, gray, and also blue, we have them in parallel laid out in the memory. Okay, so that this element, this row, is not only interacting with the first kernel, but also all the 3 other kernels in parallel. Okay, so in this way, we actually converted a convolution into a matrix multiplication. Okay, so each row is pretty bulky. It's no longer pretty. It's actually kernel size squared times C, number of elements that's going to be reduced to a single element. So what is the dimension of the output? It is actually the dimension here, right? So what is the dimension here? It's the number of windows, right? So whenever you have a window, we have a row, right? So considering the padding, this is actually the H by W, right? Considering the padding. So the output height is also H by W. And then what is output width? It is equal to the number of kernels in this case, right? So here we have 4 kernels, therefore we have 4 output channels, right? So that's exactly the output tensor dimension for the output activation, right? H by W by the output channel. So this is a very fundamental technique. Use matrix multiplication to implement convolution.
So this technique increase the peak memory usage because you increase the input activation by the width.
Yeah, exactly. So my next question I was just about to ask, what is the memory footprint compared with, for this matrix compared with the tensor over here? It's actually 9 times larger because each element is contributing to 9 different windows for a 3x3 kernel, right? So this tensor's memory footprint is actually 9 times larger, right? So the solution for that is actually using the implicit GMM, which actually we're using that for this year's torch sparse paper, rather than materializing the tensor in memory, lay out everything before computation. We just calculate them on the fly without having to lay out this piece of data in memory. But we remember where each data is in the original tensor, and we directly access the original tensor using the mapping between the location here versus the location over there. So that's called the implicit GMM, can solve this memory overhead problem. Okay, it adds a variant of direct convolution and operates directly on the input weight. The directly operates on the input weight rather than having to materialize them first into this format, which is 9 times larger and require additional memory space. All right. Let's move to the next technique, which is in place depth-wise convolution. Right? So depth-wise convolution is kind of special. There's no channel-wise reduction. Each channel is independent, right? But it's also very widely used in mobile nets and those lightweight neural networks. Let's review the structure together. Okay, so we start with a 1-by-1 convolution that increases the number of channels by 3 to 6 times, and then it runs a depth-wise convolution channel by channel. Okay, there's no reduction across the channels, but each channel is independent. Finally, it's followed by another 1-by-1 convolution. We can view it in another way. So the width of these rectangles indicates the number of channels. Okay, with smaller channel expanded by 3 or 6 times and then shrink it. So that's called the inverted bottleneck. The number of channels here is actually much larger than the 1-by-1 convolution before it and after that for the depth-wise convolution. What's the drawback over there? You also increased the peak activation by a large margin because same resolution, but the number of channel is 3 to 6 times larger than what is here, right? So that's a key problem. Since on SRAM, on microcontroller, we have very limited SRAM, only 320 kilobytes. Such large expansion ratio is very harmful, and how do we try to avoid that? So conventional method, you keep this is the input, this is the output. Okay, there's no dependency across channels. It's actually 1-to-1 mapping. Okay, so conventional implementation in TensorFlow Lite Micro, the peak memory is actually 2 times the HW times C. Okay, since we have the input, you have the output. Okay, so is that really necessary to compute this depth-wise convolution that maps this channel to this channel, this green channel to this green channel? So the output green channel doesn't depend on the red channel or orange channel or the yellow or the blue channel. It only depends on the original green channel. So is it really necessary to have 2 CHW memory footprint? Actually, it's not necessary, right? Since there's a lot of redundancy in the buffer management. we can actually do much better than that by just using one extra buffer space. Okay, we calculate the output, since the output doesn't depend on the other channels, only depend on the input channel, okay, which is channel 1, and then we write back to the original place. And then we can disregard that, since the future computation doesn't depend on it at all, right? So we can write it back and then reuse this extra temporary buffer to deal with the second channel, okay, and write it back to the second channel. Similarly for the later channels. Okay? So we only need one extra channel as a temporary buffer and write back the output in place to where it was originally located. So that requires only 1 plus C times HW of memory footprint, which actually when n is pretty large, what is the saving here? So when C is pretty large, what is the saving here? Almost 2x, right? 2C over 1 plus C.
Does this mean that this algorithm must be serial?
Be serialized, yes. But you have plenty of parallelization, since you can compute 9 elements at the same time that can already saturate the limited computation capability of a microcontroller.
This is actually trading the computation,
Right, this is actually treating parallelism for memory, right? But microcontroller, the CMD width is usually 2. You can only compute two multiplications in one cycle. So this parallelism is okay. But for GPU, this is not okay. All right, so next one, NHWC for pointwise convolution and NCHW for depthwise convolution. We actually briefly alluded this already in the beginning of the lecture, where when we are dealing with the data layout, it matters a lot whether we are doing in this direction or HWC direction. So imagine we have, this is the 1-by-1 convolution, right? So 1-by-1 convolution, if we use NCHW format, what happens? Actually, we are accessing 0 and 9 in different locations, not contiguous locations, since we are doing the reduction in the C dimension, which incurs a lot of irregular memory access and non-contiguous memory access, okay, which is hurting the cache locality. But if you store them in the NHWC format, okay, C is in the inner loop, 0 and 9, and this 81 are actually consecutive in memory, so that we can actually access different elements in a sequential manner rather than in a strided manner. Okay? So this becomes much more friendly using the NHWC for 1-by-1 convolution. What about the depthwise convolution? Okay? There's no dependency across channels. There's spatial locality if you use kernel size larger than 1, right? So if we use the NHWC format, okay, C is in this direction. Depthwise convolution need to access 0, 1, 2 consecutively. 0, 1, 2, but they are not consecutive in memory. So there's the bad strided memory access pattern, which is not cache locality friendly. But if we lay them out in NCHW format, right? So we can actually have 0, 1, 2 consecutive in memory. So the memory access pattern is much more friendly. And finally, we'll talk about Winograd convolution, which is a very amazing method that can reduce the number of floating point the arithmetic operations. Say from input to output, this is the filter. If we do the computation for one output element, how many operations do we need? We need 9 operations. Okay, but if we have C channels that require 9C computation, arithmetic operations, including actually 9C max. Right, max is very accurate since it's not necessarily floating point. Right, so we need 9C max if we want to produce only one output. Right? But if we have, we are going to produce 4 outputs that require 36C operations. Okay? We have to move the window by 4 times in order to produce 4 outputs. And mathematically, we can do such transformation to transform the tensor, the 4x4 tensor, into another 4x4 tensor using purely +1, -1, 0.5, 2. That can be done by shifting rather than rather than multiplication. Similarly, for the kernel, we can also do such transformation by having a matrix on the left, another matrix on the right, to transform it into a 4x4 matrix. And what Winograd is saying, convolution actually equal to dot product element-wise multiplication of these two tensors. Okay? Each tensor is 4x4 by C, doing element-wise product, and then just sum them up across the channel dimension. Then we get this 4x4 matrix. And then we do another output transform, having a matrix on the left, another matrix on the right, do the multiplication, which boils down to shift. It can be we can produce the final output, and they are mathematically equal. Okay, so if we not consider this data transform, which can be done by shift operations, if we just consider these matrix, these element-wise multiplications that require how many max? So 4x4 by C, so that's 16C max. Previously, we require 36C max. Now it's only 16C max. That's 2.25 fewer number of max. This is very widely used in NVIDIA TensorRT libraries, right? There's not necessarily from 3 to 4. There's also other transformations for different kernel sizes, and you can feel free to refer to TensorRT for more information. But here we are showing the transformation matrix. Why it's very cheap? Because the component is 1, 0, -1, which is very easy to calculate, just half and minus half, which can be easily done by shift operations. Okay, for all these transformation matrices, that is multiplied to the left or to the right of the original filter, original data, input data. Okay, so all these transformations can be easily implemented by shift, making it very computationally efficient. What is the drawback here? Usually, we have to pre-compute the filter transformation. It used to be a 3x3 tensor, but after the transformation, that becomes a 4x4 tensor. So that actually increased the weight size, which is the drawback. And that's the reason why we didn't actually implement this idea on microcontroller, because it's a very limited memory footprint. But this is the very important technique for GPUs.
Is this a special case of doing the discrete Fourier transform, or is this something different?
Oh, yes. Actually, this is a special case, very similar case with the Fourier transform. And another constraint is that the weight has to be constant so that we can pre-compute it, which does not apply to on-device training. So if you want to do training, this method actually doesn't apply. That's one benefit of sparse update, which we learned in last week, right? If with certain layers, we choose not to update them, the weight is constant. Therefore, we can keep this Winograd transformation, right? So we can use Winograd convolution rather than conventional convolution because the weights are constant for sparse update. So that's another benefit for sparse update that enable us to also use Winograd convolution for training, the forward pass in the training step. Okay, so that concludes the 8 techniques we introduced for TinyEngine, and that is all open source into this repo. If you go to MIT HanLab, MCUNet, and also MIT HanLab/TinyEngine, this repo actually contains all the techniques to support the neural networks here. And this is summary for today's lecture. We introduced microcontrollers, data layout for neural nets, and how to deploy them. And in lab 4, we are going to implement all to experience, not necessarily implement, but we implement a lot for you already. you can just play with these different techniques, loop and ruling, reordering SIMD image to column. That's right. And if you have any questions, you can always leave feedback or go to our office hours. And hope you can enjoy the last lab in the lecture. Okay. All right. Thank you. That's the end for today's lecture.